Hello everybody, I'm just gonna do a little quick video of the charging and discharging thing with the capacitors. I did a class video, but I talked too long and it won't load up to YouTube. So let's say you have a capacitor. It's already charged. Let's just say that there's 10 volts across here, okay? And we close this switch. What's going to happen? Well, these electrons want to get away from each other, so they zoom out of there. And they go around the circuit until it's neutralized. If we do have a resistor here, let's say it's 5 ohms. And let's say that the capacitor has a capacitance of 3 microfarads, let's say. Okay. What does this look like as it discharges? Well, we can draw a graph and we can say that the voltage over time, it will start high because you're at 10 volts here, and it'll zoom out quickly and then it will gradually taper off. Mathematically, this never reaches 0. Practically, you're gonna get really, really close, and because the universe is discrete, you're probably gonna hit 0. At the very least, you're going to hit measured 0. But mathematically never quite makes 0. We start here at V0, which for us is 10 volts, and we're going to down from there. Okay, what's the relationship here? Well, it's V equals V0 times E to the power of negative T over RC. What's RC? That is the time constant, tau. You might see this written as tau from time to time. So tau is your time constant. Okay, let me write that down. R is the resistance of the circuit, so for us it's 5 ohms. And C is the capacitance of the circuit, so for us 3 microfarads. Okay, so let's say we want to see how long it's going to take to get from 10 volts to discharge down to, let's say we're going to go down to 2 volts. How long does that take? Okay, so we got to look at this formula. We have to solve it for T. So to do that, we can bring my V0 over, and that's going to be equal to e to the negative T over RC. We could write tau here as well. We don't like this E, that's complex. So what we're going to do is we're going to ln it. We'll do that in red. It's the natural logarithm of this. And what that's going to create is the ln of E to the X is X. So anything that's up here just gets to be now on its own. But I have to ln both sides. And so we're going to end up here with ln of V over V0, which is fine. This is just going to give us a number, okay? But we do have to solve for T. So I'm going to bring that RC over. I'll put it in front of the ln so it's obvious that it's not being ln'd. And then this is going to be negative T. We want T, so we'll make this negative, and that's equal to T. So go ahead, if you're watching the video, pause it here. Try to solve this formula for T, and then using these variables, try to find out how long it's going to take us to discharge from 10 volts to 2 volts. Hopefully you did that. Now you're back, and we're going to solve this here. So I'm going to do negative, and my resistor was 5, I said, times the capacitance, I said, was 3 times 10 to the negative 6 because it's microfarads. I'm going to multiply that by the ln of V is 2 over 10. 2 divided by 10, and I press equals, and I get 2.4 times 10 to the negative 5. So if you got something close to that, that's seconds. We could turn that into microseconds if we wanted. This is going down to 10 to the negative 6, so that has to go up. 24 microseconds, we could say as well. If you got something close to that, that's grand. Now you might say, well, what does this relationship mean? To make it a little bit easier to understand, if you put this into chunks, one of these chunks is one time constant. Okay, and what happens after one time constant is, and so that's what this T over RC is, because it's the number of time constants. Sometimes that gets mixed up in my brain, and I want to write TRC because I'm thinking it's the number of time constants is the exponent here, but that's the time over the time constant. So for example, if it was 9 seconds and your time constant was 3, well, that would be 3 time constants, right? If your time was 6 seconds and your time constant is 2, then you would have 3 time constants. And that's what this is. It's the time divided by your time constant. So however many time constants is giving you the number of times you multiply by 37% or so. So after one time constant, you're down to 0.37 V naught. And then here, we have to multiply this by 0.37. So it's 0.37 squared V naught, and of course this one is 0.37 cubed V naught. So I just keep multiplying by 37%. Every time, any 2 points on this graph actually that are separated by a time constant, it'll be 37% of what you had before, okay? And this formula shows that because if you take E, if you do second divided sign, you get this little E sign. It's 2.71828, okay? So if you're wondering what is E, it's really just a number. E is 2.71828, and it keeps going. 1 over E is equal to E to the negative 1, which is, if I hit X to the negative 1, I get 0.36787. It's approximately 37%. Why that is because e to the x is its own derivative. More on that later. We'll do some more stuff with e and natural logarithms when we do atomic decays. But for now, I think it's okay if you just think of e as a number, and it's the number that is the percentage, the inverse of e is the percentage you have left after one time constant. What is the time constant? It's the resistance of the circuit times the capacitance of the capacitor. This makes sense if you look at it and you go, okay, what's R? I'm just going to do that in the corner here. R is V over I, right? And C, we said that C, capacitance is the charge per voltage, right? And so you have Q per V. And of course the V's cancel out, and that's going to equal Q over I. Well, I is current. Current is charge over time. So that you have Q over Q per T, and that just equals time. Okay. But this RC, this is a very specific time. Okay. And it's the time it takes to get to 37% of what you had before. Okay. That's for